Okay, so today we will start with chapter 1, which is about logical operators, such as the AND operator, OR operator, XOR, as well as NOT. So these are just used in computer hardware design for creating the chips or circuits. So they're used in computer engineering as well as in many software applications. So it is important for us to learn about them. So it will be propositions and logical operators, evaluating compound propositions, conditional statements, and logical equivalence. So this is what we will be discussing today. Okay, so let's look in the textbook in chapter 1. So if you got the textbook, you are able to open that. Otherwise, just follow along with me. So logic is the study of formal reasoning. And what is a proposition? The proposition is a statement that's either true or false statement. So for example, there are infinite number of prime numbers. That's true. Or 17 is even number, for false. So proposition is something that we would evaluate for whether it is a true or false statement. There could be some sentences that are not propositions. So for example, questions are not propositions. What time is it? Are you awake? So there are two possible values to evaluate the proposition. It's either true or false. So what is the truth value? The true value means that whether the proposition is actually true. Otherwise, it's false. So 2 plus 2 is 4. Truth value is true. 2 plus 2 is 5. Truth value is false. There are a couple of other things. In terms of the AND and OR operators, when we are to combine two statements together, let's say one statement is P, the proposition, and another one is Q, the second proposition. When we have two or more statements like this, we can do certain operations with them. For example, we can do a conjunction. Conjunction is when the two statements are combined together, let's say P and Q. So how about P is true, Q is true, P and Q as well is going to be true. That is both of them together. So there are certain operations that we can do with those statements. So compound proposition is created by connecting individual propositions. So let's say when we take both of those together, that's going to be a compound proposition. So the logical operation will combine propositions using a certain rule. Now we need to know whether each one of those is true or false, the ones that we are combining, right? So P, Q, and if we have others, X, Y, Z, well, we need to have some sort of a table that indicates whether those are true and false for all of our propositions. So such as over here, you know, PQ P is true, Q is true. P and Q together are going to be true as well. Now, if those were to have different values, let's say P is true, but Q is false, then P and Q together are going to be false. So if either one of them is false, or if both of them are false, then the conjunction of them is going to be false. This is the AND operator. So AND means that when we combine them together, everything we are combining needs to be true in order for the compound thing, the composition, to also be true. If any of them are false, then the compound will be false as well. So what does it mean, AND? AND means that P and Q is true only when both P and Q are true. So the AND is this sign right here. So the truth table is going to show whether the statements are true or false for any of the propositions that we are using. So let's play this animation here. So both of them are true. Oh, just a second. Both of them together, the conjunction is true only when both individual propositions are true. Otherwise, all the other possibilities will turn out to be false. So if we're thinking of this logic outside of computer science, let's say just people saying things in English language, there are other ways to have the AND operator in English language. For example, P but H, P comma H, and so on. So those would imply in English language that we using the logical AND operator. But for the purpose of computer science and for our purpose, we are just going to use literally when it says AND or it has this sign. This is the AND, logical AND operator. Okay, so this is called a conjunction when we have the AND operator. When we have the OR operator, it's called a disjunction. So disjunction is P or Q. And it is the opposite. You see, the previous sign was pointing upwards. This one is pointing downwards. So if now this is a different situation because P or Q, if either P is true or Q is true, then P or Q is going to be true. And also, if one of them is true, it is sufficient for the disjunction to also be true. So that is, if P is true but Q is false, P or Q is also true. If P is false but Q is true, P or Q is also true. So this is the opposite of what we just see with the AND operator. So in this situation, only one of them needs to be true. So when only one of them is true, the disjunction is also going to be true. Now, if both of them are false, that's the only time when it'll be the disjunction would also be false. So this is that last one right here. So P or Q is true when either P or Q are true. And it is false only when both of them are false. How about the exclusive OR? So this exclusive OR is important because, like we said, all of these are important. These are logical gates that are used, as we said, in the computer chip design for the CPUs and the hard drives and all of that stuff, but they also used in software. Like, for example, this exclusive OR is important in number of applications, including it is used for encryption and for some compression algorithms. It is also used for checking for errors, like error detections and corrections, and like parities and such. So it is important binary operation. Really, all of those are binary operations. The AND, the OR, in exclusive OR. So why is this binary? Because we take the proposition, but the only thing we record about this proposition is true or false. So really, we only need one bit to represent this thing. It's either, let's say, 0 when it's true and 1 when it's false. So this entire table here in computer science, for computer science applications, is going to be filled with zeros and ones. Let's say 0 is for true and 1 is for false. So that's why all those operations that we are discussing, logical AND, OR, and XOR, are really binary, can be done on binary numbers very easily. So this exclusive OR has many applications, like I said, in encryptions, in compression, and in error detections, and parity bits. So what is the exclusive OR? The exclusive OR of the two statements P and Q evaluates to true when P is true and Q is false, or when Q is true and P is false. So far what we have seen with the conjunction, the conjunction evaluates to true, that is the AND operator, when both of them are true. Everything else is false in all other cases. The disjunction evaluates to true whether we have true or false for them, or whether both of them are true. It evaluates to true. The exclusive OR takes only the second and the third cases here. So the exclusive OR is when either one or the other is true and false. So basically one is true, the other one is false. First one is true, second one is false, or first one is false, second one is true. That's when the exclusive OR, it's going to be true. So exclusive OR if P and Q evaluates to true when P is true and Q is false, or when Q is true and P is false. So the exclusive OR, that's what that is. There's also an inclusive OR, which is similar to the disjunction operation. So let's see here. So this exclusive OR is really important. It is denoted with a circle with a plus inside. That is the sign for it, the exclusive OR. The negation is also important. We will see in a moment. I will show you some sets so that you can we can understand better why the negation is important. So negation is when we have something. Let's say we have some numbers from 0 to 10, for example. We take the first number, number 1. And we say, number 1 not. This means all the other numbers except for the first one. So let's say we got 10 numbers from 0 to 10. If we say not number 1, this means all the other numbers are there, 2, 3, 4, 5, 6, 7, 8, 9, 10. So not is everything outside of the current proposition. So let's say negation operation acts as the negation is denoted with this sign. It means not, that is proposition not. All right, so if the proposition is true, the not of the proposition will be false, because that's the opposite of the proposition. So if the proposition is false, then the not of the proposition will be true. So the not of P is simply the opposite of P, or everything outside of P. And here is some example of what we would use those logical operators for. So let's say it can be used for database searches, for searching the web. Let's say if they search for college or university, we would get results for both topics. If we search college and college and university, dogs and fleas, then you would get both of those subjects. Can anyone see here what we have? Are you saying that you're not hearing me? Okay. Can anyone give any examples of what we would be using those logical operators for? And has anyone of you seen those before in any computer applications? So feel free to speak up and unmute yourself and speak up.
What was the question again?
Can any of you give examples of anywhere you have seen these logical operators and or exclusive OR in any of your studies or in any computer applications?
Boolean operation.
Boolean operations, very good. All right, so we will, I will show you one more thing here about the sets. And we will discuss those sets in more details later, but So just want to remind you to work on those activities here. So these are assigned for homework for this week. All the activities in the chapter, after the chapter 1.1, 1.2, 1.3, 1.4, as well up to 1.8 are assigned for homework for this week. So please read what we have just discussed here and do the assignments at the end of the chapter. So to continue with the evaluation of these compound propositions, this is the not, the and, and the or. If, let's say, a bunch of them are written like this, one after another, P and not, parentheses Q or R, then how are we to evaluate this? So the order that we would be using in the absence of parentheses is first comes the not sign, then the and, and finally the or. If we do have parentheses, then those need to be first taken into consideration. So let's say P is true, Q is false, R is true. So if we want to evaluate these right here, if we want to evaluate P and the not of Q or R, where Q or R are in parentheses, then this is what happens. First comes the F and the T. That is, the values need to be filled in first. False and true. So first comes the not operator, then the and, and finally the or. So as we mentioned, one application of those is to search Google or another search engine. So let's say for the term Jaguar, the results may include numerous things. To avoid results involving cars, if we're referring to the Jaguar animal and we don't care about the cars, then we can say Jaguar, not car. This means you give me the results for Jaguar outside of the Jaguar cars. And here's another one. P or R and the not of Q. So we would have a column for each variable and a column for the compound formula. So let's say these are the values. Then what happens? If P is true and Q is true and R is true, then what would be the result here? If all of them are true, then what would be the result of this expression? It will be false, because we're taking the negation of this and the end. Okay. So let's look at the next subject. So these are also very important because these are used, conditional statements are used in data analysis. So big data and data analytics, including machine learning algorithms, will be using those conditional operations. So this is like, let's say there is a grocery store and we go there and purchase some groceries. Let's say this is bread, this is milk. So the grocery store is recording those transactions and trying to analyze this data to find out who, if people are buying bread, they're maybe also buying milk, or people that are buying fruits are buying the bread as well. So this is like an implication sign. It means if I buy bread, I will also buy milk. That is 90% of the time that people do this according to our data. So these are used in data mining and data analysis. So the conditional operation is denoted with a right arrow. And compiled proposition can use these conditional operations. So in that situation, it will be called conditional proposition. And so this could be hypothesis or conclusion. Like I just said, if somebody is buying bread, they also are buying milk. Or if somebody is buying pizza, they are buying also Coca-Cola, unless 90% of the time, unless they are buying Pepsi, the other 10%. So what is this? This is a hypothesis or conclusion that we're making based on the data that we just analyzed. So to evaluate this, person bought bread and milk. This means the bread implies the milk. So that is true. The person came, bought the bread, but did not buy the milk. Well, what did they buy? Maybe they just bought bread by itself, or maybe they bought bread with something else, but not milk. So this is false. So then it means the bread does not imply the milk. So then the implication is false. So these conditional statements can also be used for other applications other than grocery stores. Let's say if we mow Mr. Smith lawn, then he will pay us. Again, it's an if and then statement. So if we have proposition 1, then we also have proposition 2. Now, either one of those will have a true or false assigned to it. So P is true, Q is false, then the implication can be evaluated. In data analysis, we assume both of them are true. So let's say person bought bread and milk. It's true that they bought the bread and the milk. So this means that those two items are connected, or they are associated with each other. So if both of them are true, then the implication is considered true as well. P implies Q. Mowing Mr. Smith lawn implies that he will pay you. So there are a couple of other conditional operations. So we have the if and then statement. We have if and only if. We have implies. So let's say if and only if you will mow Mr. Smith lawn only if he pays you. And then we have some other things that are using the negation with both of those. So contrapositive is when both of them are negative. So Q is the negation of Q implies the negation of P. So this means it's contrapositive. And then we have the inverse as well, which is here we have QP, here we have PQ. You see that makes a difference. Right. P implies Q is not the same thing as Q implies P, not necessarily. So that's why we have those. One is called contrapositive and the other one is called inverse. And then we have this if, which is if and only if. That is if with two F's added. So let's see here. We have this activity example of evaluating a compound proposition with biconditional. So we want to evaluate this expression right here, P or, and then the negation of Q. Q implies R or R implies Q, so both of them in both directions. So if P is true and Q is true and R is false, then what about this entire statement here? So first we will fill in the true and false values. So true, true, false. Next, parentheses come first. So this evaluates to false because one of those is false. And then we'll evaluate the or sign. I mean, so the negation and then the or sign. So negation of false is true and true or true is true. So eventually this statement evaluates to truth. And let's see the next one here. The logical equivalence. So if we have more than one statements involved, like P and Q together or P or Q, then it's called a compound proposition. So if some of them have contradiction in them, let's say they're using the negation statement, then if the compound proposition has a contradiction in it, so regardless of the true value of the individual propositions, then the compound would evaluate to false. So this is what happens over here. And the last thing we have here is the logical equivalence, which is denoted with those three lines. This is called logical, they're logically equivalent. So two compound propositions are said to be logically equivalent if they have the same true value, regardless of true values of the individual propositions. Okay, so if P is true, P not is false, then P implies not P will be false. This is the equivalent as not P implies P. I mean, this is the not P is equivalent of P implies not P. So equivalence relation really is going to say, well, the results of both of those are the same. Whatever we have on the left side of this equivalence relation is going to be the same as what we have on the right side. So that's these three lines here. Okay, so we have I have recorded this and I will put it on the website. So over here I will put up a link for today's recording from today's class, and you go ahead and read those sections. So the sections from 1.1 to 1.4 and do the activities after that. So these participation activities would be easier, the orange ones, and then the blue one is the challenge one, and there's usually only one of them for each subchapter. So do you have any questions? So you would do the activities, and then when you go to over here on the right side, click on assignments. It would say activities 1 through 3 are due. So you just do the first 4 of them from 1.1 to 1.4. If anyone has a question or anything you would like to discuss, please feel free to speak up. So the next time we will continue with laws of proposition logic, predicates, quantified statements, and De Morgan law. So that will be on Friday. And next week on Monday, it's a holiday, so there is no class on Monday, the 16th.